Well, now that we've been through the basics of both Mendelian monohybrids and dihybrid crosses, I think it's time to do some example problems. These are usually helpful because word problems are really the way to learn this. Trying to memorize a few things about the modes of inheritance and all that is great, but what you have to do is apply them. And by doing problems, you apply and you see in context what the things are that you're trying to work with. So it's a really good way to do this. And I really encourage you, now that you can completely go through the chapter on Mendelian genetics in your textbook, to work through that chapter, work all the problems that you can, look on the web. Again, be really comfortable working both monohybrid and dihybrid problems. Now, when working any problems, remember now that we've got two things going on. We've got Mendel's first principle, which is segregation, and we've got Mendel's second principle, which is assortment. We're always going to see segregation because anytime we work with even one trait, we see segregation. Assortment, we're going to see only when we have two or more traits involved or two or more loci, as we will see in the examples we're going to use today. Break the problems up. Mendel says you can do this. Mendel's Big Six and the principles of segregation say you can treat things independently. So break them apart and let Mendel do all the work that you need to be done. With any problems, we always said, first thing to do, just write down the given. Very often, half the problem or more can be solved by just writing down what information that you have. And then finally, remember that when you're working these dihybrid or multihybrid problems, do the segregation ratios first. Figure those out. Break it down to the simplest things you can do. Then you can always multiply by the product rule to get the final assortment ratios. So remember what a segregation ratio is. That's one locus, one trait. Assortment ratio is two or more loci, usually two or more traits, and they're the production of the product rule. All right, so let's take a simple example. We have tomatoes or something here, and they give you lots of information. They tell you red fruit is dominant to yellow, purple is dominant to green. All right, the following progeny are obtained from a cross, and then it says diagram this cross. All right, so clearly diagram, you're always thinking about diagram. And don't forget, we always have A times B provides C, right? So we're always looking for as much information as we can about A, about B, and about C. Well, in this case, we've gotten quite a bit, right? We're talking about diagramming. So in the future, what we mean by diagramming is to turn the modes of inheritance. Well, you're already told the modes here. One's dominant over, red fruit's dominant over yellow, and purple's dominant over green. But in the future, and a lot of problems in the textbook, you will have to figure out the mode of inheritance, and diagramming will help you do that, okay? Part of diagramming is determine the genotypes, or what is the genotype of a red, purple stemmed individual here, these progeny that are formed, as well as both the phenotypes and genotypes of the parents. You'll want to work, okay? Now this problem happens to be a bottom-up problem. Remember we said you either have a top-down or bottom-up. All right, so top down would be we give you A and B, and we ask you what you're going to produce as C. Bottom up is we give you C, and we say, go back and figure out what A and B were, what mom and dad were, or the parental units. So those are actually the easiest to work, and fortunately, that's this problem here. Now, most problems you'll find out when we get to more complicated ones give you a little bit of A and a little bit of B and a little bit of C, but you have to put it all together to work. Here's a pretty straightforward bottom-up problem, okay? Now, these are the types of questions you'd want to answer. What's the final assortment ratio here? Is it a 9, 3, 3, 1, 1, 1, 1, 1? What is it? Okay, and later on we're going to have some very complicated ones, 27 to 9 to 5 and things like that. So you can't just guess at it. You have to work through it. Okay, obviously it's going to use segregation ratios because you have fruit color as one trait and you have stem color as another. So you have two traits, at least two loci involved here. Okay, so we'll work with our segregation ratios. We'll figure out what these genotypes are. We'll figure out what the parents look like, and of course, the modes of inheritance. It's all things that should just pop into your head with any of these problems, all right? So how are we going to do it? We're going to let Mendel do all the work. This Mendel's Big Six that you have right in front of you right now, right? You have it there. All right, we're going to let Mendel do the work. How are we going to do that? We're going to first go to the principle of independent assortment, Mendel's second principle, which says that you can treat these two traits independently. You can do it. You can look at the fruit color and ignore the stem color to start. So let's do that. Let's take trait 1 and fruit color. we simply note that we have red and yellow. We might have 3 or 4 of these colors. Whatever you have, write them down. Okay, in my case, we have 2, right? We count them up, 305, 328, looks like it's going to be 630 something. And this is going to be about 207 down here. That's what we have, right? That's our data, okay? All right, what ratio fits those data? That's basically what we're after here, okay? Well, so far, we've either had a 1-to-1, a 3-to-1, or a 1-to-2-to-1. Well, there's no 2 here because you can't have a 1-to-2-to-1. There's only 2 parts. So it's either got to be a 1-to-1 or 3-to-1. And I think if you used a chi-squared or something else, we would see that a 3-to-1 is the appropriate fit. Now we're going to see some more complicated ratios coming up soon, but right now, this is the ones we work with, right? All right, so looking on here, where do we find a 3-to-1 ratio? We find it over in the phenotypes right here. We follow it back over, and we've got one type of cross. That's all you got to do, okay? That's really all you have to do. We have to say, this is a segregation ratio. It comes from Mendel's Big Six. And we just look up what cross gives that. Cross from Mendel's Big Six right here, just this page, works back over to being a heterozygote times a heterozygote that had to produce these progeny, right? Well, these are the parents, right? If they produce this and they made these progeny, this is part C, then A is this one and B is that one. These are literally the parents, okay? So we can sit there and go, okay, well, the parents from this must be a homozygous, or excuse me, a heterozygous individual here, heterozygous individual here. We know from the 3-to-1, the 3 goes with the dominant and the 1 goes with the recessive. So the genotypes here must be big A is dominant or red's dominant. So if we want to know what their phenotype is, we just look at the dominant recessive part. 3 goes with red. These guys have a big A, they're going to be red. So we're halfway through the problem. We figured out what's going on here. We figured out what the genotypes are here. This is big A blank. This is little a. And we figured already out what the parents are. Okay. Now, what do we do now? We forget about fruit color and we go over and look at stem color and we do the same thing. We look and say, okay, there's 2 stem colors, purple and green. Again, it could be 3 or 4 colors, but there's only 2 here. We count them up. We ignore what the fruit looks like and we worry about the stem. So this is 305 are purple, and looks like 110 are also purple. So we're going to look somewhere around 415, and we're going to have 328 and 97 around 425. So of the ratios we know, 3-to-1, 1-to-2-to-1, or 1-to-1, 1-to-1, right? Look on our chart. Which one produces a 1-to-1 ratio? Well, it looks like it's a one where we've got a heterozygote times a homozygous recessive, right? That's exactly what we have. We look at this as a segregation ratio. Now we want to change over to some other alleles, but somewhere we've got to have a het here times a homozygote producing that. That makes these become the parents, right? That's the cross they must be, okay? And so that means that one of them is going to be purple and one's going to be green. Now, we don't know from this 1-to-1 cross exactly which one's the dominant or recessive, but remember, we went back to the original heading when it said, oh, by the way, purple is dominant over green, right? So that was the first sentence that we saw back there. So we know that purple is dominant over green. So these guys must be purple and these guys must be green. Okay? If we didn't know that, we could just either one. We'd have to have some other information. And in these problems, there's almost that information is always provided for you. Okay, so we've used Mendel's Big Six. We've got segregation ratios, and we let Mendel's independent assortment do all the work. Now we got to put it all back together. Okay, so let's answer our questions. What are the segregation ratios? Well, for fruit color, it happens to be a 3-to-1 that we see in the phenotypes. In stem color, it's a 1-to-1. What are the most probable genotypes and phenotypes of the parents? Well, we've already figured that out. One of them has to be a het times het, and both of those turned out to be red. The other one has to be a het times a homozygote, and that turned out to be a purple times a green, which means we must have had one parent be a dihybrid het, big A, big B, little b. The other one must have been a dihybrid, but it's heterozygous at one locus and homozygous at the second locus. Okay, so one of them's red-purple, and the other one must be red-green. Okay, we don't know which one. We don't know if this was the male or the female, but in this case, without information. But others, they'll tell you dad was this and blah, blah, blah. You can figure that out. Okay, here we don't care. We just know that we've got one parent that's a dihybrid het, and it's being crossed with another parent over here that is a heterozygous at one locus, homozygous recessive at the other locus. All right. So what are the modes of inheritance? That's easy, dominant recessive, because that's all we know at this point, right? And that certainly fits with the data. All right, then we got to start figuring out the genotypes of the offspring and these final assortment ratios. Well, the genotypes are, just write them down. Given this cross, red times red, right here, phenotypically we expect a 3-to-1, so we have big A blank for red, and we have purple stems. They must be these big B, little b, okay? Excuse me, big B, little b, yes. The greens must be little b, but red. Yellows must be a recessive for the first allele, right? And purple must give you this dihybrid, or this heterozygote over here, two alleles. And then finally, we must have a little a, little a, little b. Little b is the only way we're going to get a yellow fruit with a green stem, because we were told which one was dominant, which one's recessive. That's the genotypes. What's the final assortment ratio? Well, how are we going to do that? Use the product rule, right? Big little a is 1, little b is 1, 1 to 1 is 1. Little a here is 1, so we're going to have that. But when we get up here, we're going to have a 3, right, for A, because it's 3-to-1, and a 1 over here because it was a 1-to-1 outcome. So we're going to have 3 times 1 is 3. Same thing for the second one, same thing for the third one. So this is our final assortment ratio. We expect 3 red purple for every 3 red greens, for every 1 yellow purple, for every 1 yellow green. Okay, this would be more commonly memorized as a 3-1, 3-1 ratio. We've just got it out in a different order here, but it doesn't make any difference. That's the ratio that we have. Okay, so our final assortment ratio says that. So you might make a problem for yourself that says, okay, out of 270 progeny or 350, how many are going to be yellow purple? You know, just divide it up, right? So that adds 3 plus 1 plus 8, so it's like 8 parts. So 1/8 is going to be a yellow purple, right? 3/8 is going to be a red purple. You could do any types of problems like that, right? All right, let's take that and extend it to genotypes. We were talking about phenotypes there, what a 3-to-1 ratio and things. So we're way over here in this column as an answer. But what if we move to this column, right? What if we're talking about genotypes, and that becomes important? Well, it's the same issue. If we want to do that, let's take this dihybrid heterozygous cross, so doubly heterozygous cross, all the possibilities, okay? Well, I can tell you that it's going to be a 1 to 2 to 1 to 2 to 4 to 2 to 1 to 2 to 1 outcome, but you don't need to memorize that, okay? Why? Because you can let Mendel do all the work. For the A locus, we're crossing a heterozygote times a heterozygote. Genotypically, we're getting a 1 to 2 to 1. For the B locus, we're doing the same thing. We're just changing the letters. We're going to put all those together. You could do a Punnett square if you want, but we could certainly put big A with everybody that's down here and just simply write them down, okay? Carry their numbers with them. So 1 for big A, 1 for big B, 1 times 1 is 1, 1 for big A, and 2 for big B, little b, carry that down, multiply it out. Then we just come back and do the same thing. We grab this one here, write it down with all possible outcomes, and write the numbers down, right? So 2 times 1 is 2, 2 times 2 is 4, 2 times 1 is 2. And then finally, we just grab the last one and write it down with all possibles, and we end up with this. So our final ratio here, final assortment ratio, it's assortment, right? Because we're dealing with 2 loci in this case, happens to be a genotypic assortment. Phenotypic assortment would be maybe a 9-3-3-1 or whatever. Notice that it adds up to 16 parts. If we do all the math of 1 plus 2 plus 1 plus 2 plus 2 plus 4, that's 16. 9 plus 3 plus 3 plus 1 is 16. All adds up to the same thing. It's just that this is genotypic, not phenotypic, okay? And if you want to make sure you know how many of these groups down here you ought to have, you just simply take the total number from up here, 1, 2, 3, right? 1, 2, 3, multiply those out. I should have 9 major groups, and there they are. 1, 2, 3, 1, 2, 3, 1, 2, 3, 9, okay? So I've taken nothing but my segregation ratios, genotypic in this case, multiplied them together by the product rule, and I get my final assortment ratio, which happens to be genotypic. Again, no reason to memorize 1 to 2 to 1 to 2 to 4 to 2 to 1 to 2 to 1. You can make it in seconds anytime you want to. Okay. All right. So that's your final ratio from all of this, and that should end this. All right, so that's working a couple of problems. I think we'll do another lecture, a short lecture like this, working a few more problems, kind of see, make sure you can and see going from the other direction how it might work.